This week, we're going to have both Zach Sunberg today and then Shreyas Kosick on Thursday. And Zach did his, he did his PhD at Stanford with Professor Michael Kokendorfer. And Michael Kokendorfer is this everything's a Pomdp. We solve everything in the world using partially observable Markov decision processes, a fanatic, and managed to, convert Zach to this, also with Julia as a code base. And then Zach joined my group at Berkeley for his postdoc and explored a lot of things and shared a lot of knowledge about POMDPs and thinking about POMDPs and reachability and the relationships between them. And now he's a professor at CU Boulder in the Aero-Astro or Aero-E type department. And he's doing a lot of cool work in terms of safety using POMDPs. And so given that, I will go ahead and pass it over to Zach. Zach, do you prefer in terms of questions, do you prefer people just saying them out loud, chat, waiting?
I think let's if you have a question, interrupt.
Okay.
So yeah, I think there could be, it's hard to come into, or there's a lot of different backgrounds that you could have. So connecting them all takes a lot of back and forth. So I like to tell my students that they should think of themselves as being on a team, having a team effort of extracting knowledge from me. So asking questions is a great thing. And I think, so if there ends up being an interruption and discussion, that's great.
Okay, good. Last time we got a lot of good questions from the students, so hopefully they will not be shy.
So I also shared in the chat, I don't know if maybe you might want to copy and paste it again in case anybody joined it later. So I have this little worksheet. So just these 6 things are things to pay attention to in the first kind of third of the lecture, maybe. Make sure you remember what those things are when I talk about them. And then we're going to have a little breakout room exercise where we'll talk about kind of how to formulate problems as POMDPs. Cool. All right. So today I'm going to talk about safety and efficiency through POMDP planning. So I think a lot of you, probably if you're in this class, most of you are concerned with this question about how do we deploy autonomy with confidence, and there's all these different applications from autonomous vehicles to space vehicles to, drone delivery or manufacturing, or even just kind of a personal assistant in your home. And the aspect of that I'm going to talk about today is both safety and efficiency through online learning. So there's a lot of objectives for autonomy. You could, make a huge list of these, but today I'm going to focus on 2 of them, which are safety, which is minimizing risk to yourself or others, and then efficiency, which is minimizing resource use. So especially time is often our most valuable resource. The problem is these 2 objectives often oppose each other. So there is one way that we could be totally safe. We would never have any accidents, any problems, and that is just to stay home. But that's really unsatisfactory because then we never accomplish our goals. We never do the things that we set out to do. The other end of this spectrum would be something like this, where you just go for it. So you maximize efficiency, don't worry about safety at all. But this obviously isn't, good either, because we would cause a lot of damage doing this kind of stuff. So what we really want is a sophisticated trade-off between these. So one way of kind of analyzing or dealing with this trade-off is through Pareto optimization. So in Pareto optimization, you have 2 goals, in this case, safety on the x-axis of this graph and efficiency on the y-axis. And you have some kind of objective J that you're trying to maximize. And in Pareto optimization, you have 2 terms, or multiple terms possibly, one for each of your objectives. And then you have this weight lambda that trades off between them. So by just adjusting lambda, also I should mention that in general, better performance on this graph is up to the right. We want safety and efficiency. But with a given model of the world and a given algorithm for analyzing or for solving this optimization model, just by changing the weight lambda, we can move along this purple curve that I have here. Can you guys see my pointer? Yeah. Okay. All right. So if we have a large weight lambda, where do you think we would be on this curve? Anybody can type it in the chat or just speak up. If lambda is large, where along this curve would our solution be?
Right, bottom.
Yeah, exactly. So a large lambda would be in the bottom right and a small lambda would be in the top left. So this is just a way of talking about the trade-offs between safety and efficiency. Now, the question of where we should lie on this curve is kind of a philosophical question or maybe a policy question that I'm not going to focus on too much today, although it is a huge important question. But what I'm going to focus on is how we can use better models and better algorithms to move this entire curve up and to the right. So by dealing with uncertainty better, we might be able to have the same level of safety. So like these 2 points have the same level of safety, but this new model and new algorithm have a higher efficiency for that given level of safety. So let's talk about how to do that. To have this conversation, we need to classify uncertainty into multiple types. So the first type is called Alliatory Uncertainty, which basically means you can't learn anything about the outcomes about future outcomes by observing past outcomes. So an example of this would be a coin flip. Every time you flip the coin, it's just 50% heads, 50% tails. The next type is epistemic uncertainty. And so epistemic uncertainty means that after observing some outcomes, you can learn more about the future outcomes. So an example of this is a weighted die. So this cutout just reveals what's inside the die. It's not actually cut out. But if you say you had a weight on this side with 3, then that would make it more likely for 3 to be on the bottom and whatever's on the other side to come up. So initially, when you roll this die, you might think all outcomes are equally likely, but after rolling it a bunch, you can learn that it's weighted in one way and it's more likely to have certain outcomes. So that kind of uncertainty that you can learn about is called epistemic uncertainty. And this is an example of static epistemic uncertainty because the weighting of the die can't change as you keep going through. There can also be dynamic epistemic uncertainty, which you could think of as like a deck of cards, a hand of cards. You have these cards in your hand or on the table that you might not be able to see, but by observing how other people play or observing which ones come up, you can learn gradually what's in the hand, but it might also change as the game goes along. So those are kind of 3 classifications. I also think you guys have been making a distinction between like worst case and probabilistic uncertainty. I don't know if did you have different words for that? Okay, yeah.
It's fine.
What different words did you use? I can't remember.
What do we use? We used non-deterministic or bounded versus the probabilistic.
Yeah, so all of the uncertainty that I'm going to talk about today is going to be in terms of probabilistic uncertainty rather than bounded or worst case uncertainty. Okay, so in order to formulate this as a sequential decision problem, formulate a problem with uncertainty, our primary kind of formalism or tool is the Markov decision process. So in a Markov decision process, you have some dynamics. This is kind of a control theoretic type notation. You have a state at time +1 is some function of the state at time t, an action at time t, and some noise, wt. So this means that there's some dynamics that you know, but there's also this noise, which is aleatory uncertainty. Assuming that all wt are independent, then this is aleatory uncertainty. that flows into your system. And the goal is to find a policy, pi, which is a function that maps every state to an action. And the objective is to maximize the, this is a bad typo. This gamma should be raised to the t. It should be gamma to the t, which is a discount factor, which makes less rewards far into the future less important than current rewards. But our goal is to maximize the expectation of rewards at all time. There should also be an expectation out here.
Question about gamma. Is gamma less than 1?
Yes, gamma is less than 1. I don't know what the implications of a gamma greater than 1 would be. I mean, your objective would be infinite in that case. So it wouldn't make that much. It would be kind of an ill-posed problem. Okay, so yeah, this should be expectation of gamma to the t. Another way of kind of thinking about a Markov decision process is in terms of this for tuple STAR, where S is a state space, which could be infinite, or in this case on the left, it's just finite. It's got 1, 2, and 3 different states that the system can be in. So it's a discrete state space, whereas in the last slide, it was an infinite state space. MDPs encompass both of those. A transition probability distribution, which maps T, so T maps the probability of starting in a state in the state space, taking an action, and landing in another state to a real number that represents the probability of that transition. So for instance, in this diagram, if we start in state 3 and take action B, then we have a 70% chance of returning to 3 and a 30% chance of going to 2, and then a reward for every state and action pair. So if we start in state 3, take action B, with a 30% chance we get a -10 reward, or with a 70% chance we don't get any reward. So those are these two ways of thinking about MDPs are equally valid. They can have continuous state spaces or these kind of small discrete state spaces.
A quick question. In the first one, you had a continuous state space, continuous action space, but discrete time?
Yeah, discrete time. So there are continuous time Markov decision processes, but that is more of theoretical interest. So most of the time we do discrete time. So good.
And then
good
in the
question.
second one, you did discrete states and discrete actions.
Yeah. Okay. Yeah. So with a partially observable MDP, a Pomdp, we keep the same state dynamics. We still have the same state dynamics. We still have the same objective with the same typos. And then, except now, instead of being able to observe the state exactly and building a policy off the state, instead we get observations, which are some function h of st, at, and the new state with some noise vt. And so now the policy doesn't depend only on the current state, but optimal policies might have to take into account all of the actions back to time 0, or all of the actions and observations back to time 0, which is sometimes referred to as a history, because some of these observations could encode useful information. So we can also look at a partially observable Markov decision process in this kind of discrete paradigm where we have ST, A, and R are the same as an MDP, but we now add an observation space O and an observation probability distribution. So the observation spaces, the observations aren't shown in this drawing, but we just have question marks now because we don't know for sure what state we're actually in. So here's an example. So this is a one-dimensional light-dark problem. There's all kinds of different light-dark problems that people in the Pomdp community talk about. But this actually is kind of a sort of safety-conscious problem here. So here, the state space is Z, which is the set of integers. It's like all the way from -infinity to +infinity. So you can be in any one of those states. S prime equals SA. So we typically use this prime notation to indicate a variable at the next time step. So this is just saying our state transitions are actually deterministic. There's no noise in them. We just take an action A and deterministically transition to the next state. And then our observation is normally distributed with a mean around the true state and a standard deviation that this should actually have an absolute value on it. A standard deviation that's 0 at state 10, but expands as far further as it gets further away from state 10. So in this light region, we get accurate observations, but in the dark region, we get poor observations. So we don't know what state we start out in, but if we can localize in the light region, then we'll know where we are. The actions are, we can either take like a big jump, -10, -1, stay in the same spot, 0, or take a -1 or 1 small jump, or a +10 large jump. And then the reward function is +100 if we take action 0, this special action 0, in state S0, and -100 if we take action 0 anywhere else, and then -1 for every time step that it takes us. So the reason that I say this has like a safety flavor is that this goal is to take action A at state 0, which is like a really precision oriented goal. If you take action A anywhere else, you'll get a huge negative reward. So that's unsafe. Whereas if you take action A at state 0, if you know exactly where you are, then you get a really big positive reward. And then this -1 kind of encodes efficiency. So like I said, there's accurate observations there. The optimal policy looks something like this. A policy, well, a trajectory under the optimal policy looks something like this. So you go up until you can localize yourself in the light region, and then you come down and take action A equals 0 once you're sure that you're there. So does anybody have any kind of questions about this Pomdp formulation? Cool. All right, so let's talk about how we actually interact in a Pomdp and how we would go about planning in it. So in this environment that we have, there's some true state, S equals 7, for instance, that we don't know. At every time step, we get an observation, for instance, -0.21. And then so you don't necessarily have to do this to solve a Pomdp, but one of the most useful things we can do is come up with a belief, which is a posterior probability distribution of the state conditioned on all of the previous actions and observations. So BT of S is the probability that ST equals S, given all the information that we've received. And through Bayes' rule, we can conveniently show that this is proportional to the probability of that observation multiplied by the sum of these transition probabilities times the belief at the previous time step. So this this Bayes' rule update allows us to get a distribution over where we think we are in the Pomdp, and we can make decisions based on that. That distribution is the probability that we're in that state. And then from that, we can execute a policy and take an action, and that changes the environment. Then we get another observation and update our belief, and that will allow us to operate efficiently in this Pomdp. So that's kind of the gist of what a Pomdp is. We're going to jump into breakout rooms for a couple minutes just to see if we can kind of formulate or kind of talk about some of the aspects of a Pomdp. And I didn't talk at all about the second half of the lecture, which is how do you come up with these policies? So let's hop into breakout rooms. I'm not sure if you can do that, Sylvia, maybe like 3 or 4 people per breakout room.
Okay.
And so I have on the second page of this worksheet, I have this, this breakout room exercise. So we have a hospital considering how to test and treat cancer patients. Cancer can have 2 stages, in situ and invasive. And the doctors have a test with 85% accuracy and 2 treatments. The questions I want you to think about are, how would you define the state's actions and observations of this as a Pomdp? How would you define the reward function? Or like, what is kind of an example of a reward function? What are examples of aleatory and epistemic uncertainty? And then think about a heuristic policy. So if you have a policy that maps either histories, i.e. observation histories, or beliefs to some action, what might that look like? So I think 5 minutes should probably be, or maybe 6 minutes should probably be good enough, and then we'll come back here and discuss.
I think, Zach, I think you will be sent to a breakout room as well.
Okay.
I don't know how to undo that, but you might be able to move around from there. Okay, here we go.
Thanks.
Okay, now it's recording again. If you need host back, just let me know.
Okay, cool. And the class ends at 1:50?
Yep.
Okay, cool. All right. Is everybody back? Is this everybody?
I think so.
Let's see. All right. Cool. Great. All right. So let's talk through your answers. It sounded like everybody kind of had a pretty good idea of what was going on. So I'm gonna share my screen and kind of draw out as we talk. So how about somebody from breakout room 4? What did you think would be a good representation of the state space? And by the way, these answers are very subjective.
Do they know which breakout room they were in?
I don't know. Do you guys know which breakout room you're in?
4 was Muhan, Nikhil, Bakira, and Yuhao.
We think the state might be the stages of the cancer.
Yeah, okay. Yeah, I think that's a good representation or a good thought. In situ, or what was the other one? Invasive.
Invasive, yeah.
Yeah, okay. So that would be a good, yeah, that would definitely be a good representation for a small state space. I saw one team also talked about like the concentration of cancer cells. So then you would have a continuous state space, which might also be a good state space representation. So I thought those were all good thoughts. So how about group, or somebody else from any group, what did you choose as the action space?
Treatment A and B.
Yeah, okay, so like testing, tests, you can run a test, or you can treat A, use treatment A or treatment B. Yeah, I think that's good.
Or do nothing.
What's that?
Or do
Or
nothing.
nothing. Yeah, exactly.
Deficient is
why
harder.
might do nothing be a good action?
So if you're in the no cancer state, then there's no point
Yeah.
introducing side effects when you're fine. Patient is fine.
Right, exactly. So this is kind of a, safety versus efficiency thing. You don't want to intrude in people's lives. And also another perhaps more important factor is sometimes if we'll talk about this in the reward function. So T, I won't, make us describe because that'll take a lot of talking, but basically, there's some probability of going from cancer to in situ and in situ to invasive, each year of the problem that you're doing this. How about the reward function? Who has thoughts on the reward function?
I think it's in high level, it is basically penalize more for more severe cancer and penalize more for treatment with more side effects and plus the two terms.
Okay, so minus some number or negative reward for severe cancer. Okay, I like that. Negative reward for severe cancer, negative reward for invasive or
aggressive treatment.
Yeah, aggressive. Yeah, that's a good. Maybe like plus one for doing nothing, just having a normal life that year. I think
Question,
Can
we combine like the actions? So like the reward function, making it a function of the state and the action. So there should be it shouldn't be as bad if the cancer is severe and you're taking actions to cure the patient, as opposed to having severe cancer and doing nothing. Right?
Yeah. So right, exactly. So so there's a lot of different ways you could define this, and this is this is complete. I'm going to mention this as one of the outstanding problems in this whole field is how do you choose the reward function? And there's a whole literature about this and a ton of research, and it's generally called the alignment problem. How do we align artificial intelligence with what is actually good for us? So another reward function to consider might be like +1 for every year of life without treatment or cancer. And then, -100 for, well, actually, I don't even know if you would, so this might be a good enough reward function, and then like plus 0.5 for a year of life with invasive treatment, something like this. And then if a patient actually dies, then you don't get any more years of life, so that disincentivizes that. So the reward function is very subjective. There's a lot of ways you can do it, but I definitely like what you guys said. So let's see, what were the other questions? So what are examples of aleatory and epistemic uncertainty in the problem? Who has a guess for that?
So for epistemic, we thought it would be the tests and the probability with which they'd give the accurate result. And for
so can you explain that more? So how would you, so epistemic uncertainty is something that you can learn about by observing outcomes over time. So how would you learn about the probability of the test?
Oh, sorry, my bad. Then I think I switched them.
Oh, okay. All right.
Yeah.
That's what I thought. Yeah. So, okay. Yeah. So yeah, you can't really, with the test outcome, if it's only 85% accurate, you can't really learn that much about it. And then what's your guess for what's epistemic?
For epistemic, I think we were thinking like their reaction to the treatments.
Okay.
So probability of like having adverse side effects.
Yeah. Okay. Cool. Yeah, I like that a lot. So like after you've treated them once, you can get an idea of what their side effects are like, and then you might, instead of your reward having, being a function of just the treatment, you could have another state in here, which is like, what's their side effect reactions, and you could say, you could put a negative reward for worse side effects. And then you kind of have to like try out different treatments, see what their side effects are. And since that's epistemic uncertainty, gradually you get better at it. So I like that a lot. Maybe one takeaway here though, is that almost all uncertainty doesn't fall clearly into one of these categories in the real world. So even the test outcome, you might learn that, it's really accurate for these particular cases and really inaccurate for some other particular cases. So you might be able to learn over time. But usually it's still useful to have these two categories in discussing this with other engineers and problem solvers and stuff. Great. Let's see, what was the, a heuristic policy. So did anybody come up with kind of a heuristic policy for how you would manage this cancer treatment?
I mean, in my group, we thought of when we had the concentration thing. When the concentration of the patient's cancer cells is very high, then you use the medication B, the one with the high side effect but higher chance of working, but contingent on the fact that the side effect is not as bad as the patient being highly infested with cancer. So there has to be some relative severity. What is worse, the side effect or the cancer itself? So we're assuming the side effects aren't as bad as the cancer itself, in which case, if your concentration is very high, use medication B. As the concentration decreases, use medication A.
Okay, nice. Yeah, I like this a lot. So then my comeback question is, do you know what the concentration is?
We're assuming the test can give us that information somewhat accurately.
Okay, so maybe after some testing, which gives you observations about, how much cancer there is, you can get a belief over the concentration, and based on what maybe the mean of the belief is, then you can decide whether to use B. My other question for you then is, you said use B only if it's not as bad as having cancer. So say, is there any case where, say I'm trying to decide whether to use B for the next 6 months. Is there any case where it would be right to use B even if it's worse than having the cancer for those 6 months?
If there's a guarantee that at the end of those 6 months, the person becomes maybe cancer free. So and this is a very horrible example. Say the side effect is you being brain dead, right? The person being brain dead, right? But then after 6 months, the cancer disappears and they're back to life, right? In those 6 months, brain dead is worse than having cancer. But if there's a terminal reward that's so high that after 6 months you're back to life, you're doing everything you want to do, then yeah, maybe being brain dead for 6 months isn't so bad.
Yeah. Okay. I like that a lot because it really gets at one of the key concepts for solving these MDPs and POMDPs is trading off immediate versus long-term reward. So let's hop back into the lecture. Any more comments or questions about this kind of cancer problem? Okay, cool. All right, so let's talk about how to actually solve these. So one important concept is a value function, which I think you guys have covered in some sense. But the value function is this v pi of s, which is the expected sum of rewards over the future. So this accounts for both the current reward and the discounted long-term rewards. So whenever you think about immediate versus long-term rewards, in immediate rewards, you should think about the reward function, and long-term rewards, you should think about the value function, which unfortunately, there's a lot of different notations. And some people use V, most people use V, some people use U, and then we'll also talk about something called the Q value in a second.
So I have a quick question, Zach.
Yeah.
So in our lectures, we've been talking about the relationship between using a value function that has an average or cumulative reward versus a value function that does like the minimum reward over time. Like we often do in reachability, we're looking at the worst case. What's the relationship here and the implications on how you're thinking about safety?
Right. So this is the expected reward over future time, which when you're thinking about safety, I will talk about this later, how this is potentially a weakness. This can be very dangerous to use the expectation here because you might have a low probability of something very bad happening. And there's other ways to deal with that, but we'll talk about that as a weakness in terms of safety towards the end of the lecture. But that's a good distinction to make. Okay, so like I said, the value is the expected sum of future rewards. Solving this problem straight up is hard because you have this infinite sum over all time. Luckily, there's this equation, which is probably my favorite equation. It's called the Bellman equation. And this simply says that the value, the optimal value, so this is the value for a particular policy. This is the optimal value function. So the value function for an optimal policy is equal to, at every state, is equal to the max over the immediate reward plus the expectation of the value at the next step. And the beautiful thing about this is that this only involves 2 time steps. So it involves the value at the current time and the value at 1 time step into the future. And this Bellman's equation allows us to break this huge problem of solving for all infinite time into the future into smaller problems. Another thing to note is this term of the Q value, which is also called the state action value. So the Q value is the expected sum of all future rewards, except given that you take action A. So the V value is for only a state and the Q value is for a state in action. So this Q value shows up within this maximum here. All right. So any questions about these value functions? No. Okay. So now I'll talk about kind of our go-to tools for solving MDPs. So these are fully observable problems. Offline, we have an algorithm called value iteration that I'll cover on the next slide. And then online, we have Monte Carlo tree search. Monte Carlo tree search is a particular kind of tree search that is not always the best, but it's my go-to tool for this. So value iteration is a very simple algorithm that basically just says repeatedly apply this Bellman equation. So we start with a value function set to 0 for all states, and then we repeat this Bellman backup operation. So for each state S, we just solve this Bellman equation. We say the new value at state S is equal to the max over A of the immediate reward plus the expectation. And this is just the expectation expanded out into a sum of the old value, UK, at the next state. And I'll show you this in a picture on the next page. And then we just repeatedly apply this Bellman operator until UK and UK plus 1 are close to the same. And then we have the optimal value function. And once you have the optimal value function, you can easily read off a policy because you just take the action that maximizes the immediate reward plus the expectation of this future optimal value function. Okay, so let's see what that looks like. So this is what's called a hex world And really, most people use grid worlds because they're easier to think about. But this was the easiest one to get a picture of. So this is iteration 0, and there will be colors that represent the value function. So in this problem, it's not noted here, but there's a positive reward in this cell. The cell or the state is which of these cells you're in. The action space is take any direction action, and you'll go in that direction with high probability, or randomly you might go in another direction. And then there's a negative reward in one of these. So right now we start out with the value function initialized to 0. After one iteration, we basically just get the reward states in the value function. So this is plotting the value function, and we see we have a negative value right here, a slightly positive value here, and then a very positive value here. And then we simply iterate on this. So now we've backed up the value function. So we've said, now we've spread this value out for one step and taken the max over it. So the reward from this cell is kind of spreading out as we do more iterations, and the reward from the high reward cell is spreading out backwards and backwards. And eventually you'll get to a steady state value function, which is the optimal value function. You can use contraction theory to prove that this will always converge to the optimal value. So this is your go-to algorithm for solving MDPs offline. Shoot, I need to back up for a second. So another important concept here is the difference between an offline and an online solution. Does anybody know what the distinction there is? Okay, so in an offline solution, we calculate the policy before we get into the environment and are interacting with it. We think about all the possible states we might be in, calculate a policy for it. Whereas online, we only calculate a policy for the current state we're in, but we do that online based on the states that we're likely to reach in the future. So offline is nice because you can pre-compute it, you can test the policy, you can be 100% sure that you have the optimal policy before you interact with the environment. But online methods can handle much larger problems because you're not trying to solve for the entire state space. Okay, so here is an example of an online method. So I've just rewritten the definition of this Q value here. And then the value function v, and then this is our picture of an MDP from an earlier slide. So you can take this and kind of rearrange it into a tree where there's alternating layers of state and action nodes. So this is imagine we're at state 3 and we're trying to choose whether to take action A and B. We have this kind of tree that encodes all of the consequences of our future actions. We have, if we take A, we'll transition to 1 and we'll get -5 or +5, etc. So this is just rearranging that. Now, if we estimate the Q values at all the action nodes and estimate the V values at all state nodes, then all we have to do to choose the optimal action at state 3 is to take A or B, whichever has the highest Q value at state 3. Now, there's a problem with doing this because this tree is exponential in the time horizon. So the further out you want to plan into the future, you get an exponentially larger tree. So that's an intractable problem to solve. So that's why people use this algorithm called Monte Carlo tree search, which focuses the search to both promising and likely parts of the tree. So this has 4 different steps. Selection, you have a partially built tree that you're starting with. You choose a route through the tree based on some exploration and exploitation policy. Then you expand the tree, you add 1 new node, you do a rollout to estimate the value at that node. A rollout simulation means just simulating out for a certain number of steps with a default or random policy. And then you back propagate all of the Q values and V values back up to the tree. So this Monte Carlo tree search allows you to do a very focused and efficient search of this tree, where you only care about the parts of the tree that are likely to be reached and are also promising. All right.
Can you emphasize one more time what rollout and what backup means?
Yeah, okay, so the rollout means, so when we add a new, simulation is what they use here, but I use the word rollout. So when you add a new state node here, you need an estimate for the V value at that state node. So what you do to estimate that V value is you run a single Monte Carlo simulation. You have a default policy pi 0 that you simulate out for 10 or 100 steps, and that gives you the estimate of what the value is at that node. Now, the back propagation just means that you repeatedly apply these two equations. So you start down at the new node that you just added, then you calculate, so you've got the V from the rollout, then you calculate the Q based on this equation. So you calculate the Q for action A at state 2, then you calculate V at state 2 for this, and you repeat these equations, working your way back up the tree, back to the root node. So that's if you don't understand how that works in this lecture, don't worry. It's a bit complicated, but the basic takeaways are, we've got this tree, we want to estimate the value functions in it, and we want to focus our search with Monte Carlo tree search. Okay, so when we go to Pomdps, we have something kind of similar. So offline, we want to use something called point-based value iteration, which is basically a more efficient way of doing value iteration in Pomdps. And I'm not going to talk about that. You can solve problems up to maybe hundreds of discrete states, maybe 1,000 discrete states with this algorithm called SARSUP. But it's typically, since PomDPs are very computationally intensive, it's hard to get offline solutions. What I'm going to focus more on is online, where we use the same Monte Carlo tree search algorithm, but slightly modified. So to talk about how it's modified, we can remember we've got this environment, we've got the belief updater, and then we've got the policy. And in an online algorithm, instead of having a pre-computed policy, we create one of these trees at every time instant or every time step to get an idea of what we should do at the current belief. Now, I've tried to make this look like a belief. So these orange things kind of look like skewed Gaussian distributions or something. And those are to emphasize that now, instead of these circles corresponding to states, they actually correspond to beliefs. And one of the problems with doing tree search in PomDPs is that it's very computationally intensive to calculate these belief updates at every point in the tree. So we can, so another way of saying this is that a PomDP is an MDP on the belief space. So every time you get an observation, you can do your belief update with Bayes' rule or with a Kalman filter that gives you a new belief. And this PomDP is actually an MDP on the belief space. So instead of moving around to different states, the agent is moving in its mind around to different beliefs about the state. So this is what the tree looks like I said, in a PomDP. But people realized in about 2010 that this was really inefficient. So there's this new algorithm called PomCP that they came up with, that instead of doing complete belief updates at every time step, it just runs state trajectories down through this and then represents the beliefs by unweighted sets of particles. So this is similar to a rejection sampling particle filter. So this is your basic, this PomCP algorithm, which stands for partially observable Monte Carlo planning, is probably your most basic effective PomDP planning algorithm. Probably what you want to start off if you're planning in a PomDP. So let's put this in a more real world example. So we've got autonomous driving, which is what I worked on in the second half of my PhD. So we focused on this problem. So this is a Waymo car in California. It's getting on the highway. It might be taking somebody to work or something, you know. It turns on its blinker to get on the 101 here, and it's trying to get over. So it's being safe. I want to recognize that they've done a great job of safety on this car. There's no chance of it crashing, but unfortunately, it is not able to get onto the road, and so it has to take this exit. And then, you know, it may not, the passenger may not get to work on time. Like, this could be a huge problem. So this really, we thought that this really captured this trade-off between safety and efficiency. Autonomous cars have a huge, like, there's a bunch of opportunity for improvements in safety, but only if they're efficient enough for people to use them. Because if you can't get to work on time, people won't use it. So our hypothesis was that we could reason about the epistemic uncertainty in other people's drivers' behaviors and improve both safety and efficiency simultaneously. So these internal states, we assumed that you can measure all of the external states accurately. So you have a LiDAR or something on your car, you can measure the position, velocity, you can look at the turn signals. But the internal states represent partially observable states that are epistemic uncertainty. So we used this thing called the intelligent driver model to model the internal states. This is a differential equation. It governs how the drivers behave based on these internal parameters. So an example of one is like the desired speed, where for an aggressive driver, that might be, you know, 40 meters per second. For a timid driver, that might be, you know, 28 meters per second. These values were taken from some real road data. So this model is a model for how other humans drive based on these 8 parameters. And if we put Monte Carlo tree search or this Pomdp algorithm, and we implement a version of it on our vehicle, it might look something like this. So this is an overhead view. The green car is the ego vehicle that we're controlling. The red and blue cars are other vehicles. And the redness of the car indicates its aggressiveness. So red cars are really aggressive, blue cars are really timid, but we don't know what that is yet. The white lines are our potential plans that we're considering. And these red and blue lines are our predictions of what the other cars are going to do. So each branch in the tree contains one of these white lines along with a bunch of red and blue lines. So as we go along, okay, there we go. So as we go along, you can see we're planning. As we observe the drivers, we get more and more convinced of their true kind of internal disposition. So before, at the beginning, we had red and blue lines coming off of almost all the cars because we weren't sure if they were timid or aggressive. But now that we've observed their external states for long enough, we're able to infer. And so like now at the end, all of the predictions coming off the red car were red. So they were aggressive predictions, and all the predictions coming off the blue car were blue, for instance. And so with this Monte Carlo tree search algorithm, that actually was in real time. It takes about half a second to construct the entire tree and make a decision. And we were able to, achieve our objective of doing 4 lane changes within 1,000 meters. Now, this is augmented with, so in terms of safety, this is augmented in with kind of a, I don't know if it's technically called a control barrier function, but it basically says, if you can't ever take an action that will get you into a situation that you can't get out of, given that the other cars follow this IDM model. So there's a lot of kind of details buried there. But the main point of this work is not actually ensuring safety. We assume that we have another controller doing that, but avoiding getting into potentially unsafe situations while also being efficient in planning how we're going to execute our lane change. So again, this idea that there's this trade-off between safety and efficiency, and if we're not efficient enough, people won't use our algorithm or our control system, no matter how safe it is. So that looks cool. Qualitatively, we were able to accomplish that lane change, but we also wanted to see if it was it actually made a quantitative difference. So this graph shows safety on the x-axis and the fraction of successful. So safety, like I said, doesn't actually involve crashes. It says if any hard braking actions occur for any cars, not just us, then that's considered an unsafe situation. So if anybody brakes at more than 4 meters per second squared, then it's an unsafe situation. And then the y-axis is the fraction of times that we were successful in doing this 4-lane change maneuver within 1,000 meters. So we could consider 2 Mdp models. There should be, these are both Mdp models, but one is kind of an over-optimistic model. So that's the blue here. And this kink, in an ideal situation, this kink wouldn't be here. It would be like a convex function. But there's a reason for this, and it's in the details. But the basic idea is if we assume all drivers act normally, then we can get a pretty high success rate. So we're efficient, but we're not safe, because in real life, a lot of drivers are aggressive or timid. And so that results in unsafe situations if we assume that they're normal. Now, the other thing that we could do is have an Mdp, where again, we're not considering the internal states of individual cars, but instead we're learning from data and saying essentially that at any time step, any car could have the internal states of an aggressive driver or a timid driver. And that just changes with equal probability at every time step. So this is like modeling all of our uncertainty as aleatory, with the blue line being an over-optimistic estimation of what other drivers will do, and the red line being a pessimistic estimation of how the other drivers will behave, or maybe a robust estimation. So as you can see, these, the red one allows us to be more safe, but less efficient, and the blue one allows for more efficiency, but less safety. So the first question to ask is, can we do better if we somehow magically knew the internal states, if there was no epistemic uncertainty? And so we did this test. We imagined that we knew exactly what the internal states were magically. We were omniscient, and we got this curve. So there is a big gap here. And then the next question is, can a Pomdp planner actually close this gap? And it turns out that we were able to in this simulation setting. So with the Pomdp planning, we're not able to plan as well as the omniscient planner, because we still have to rely only on our belief, not true knowledge of the internal states. But we're able to almost close that gap. So that could mean like a big jump in success without compromising safety at all, or a big jump in safety without compromising efficiency. So does anybody have any questions about this part, like what this result means?
I had a question regarding kind of the convergence of your drivers to aggressive and timid. So if you have a very oscillatory driver who operates in one regime long enough for your algorithm to converge its belief that they're timid or aggressive, and then they switch, how do you guys deal with that sort of particle depletion of maybe your aggressive set versus your timid set?
Yeah, that's a great question, and that gets right to the heart of it. So we for this study, we assumed that that for each driver, the internal states never changed. But like you said, there definitely could be changes in that. And so the way that you can, so that's the difference between static epistemic uncertainty with a weighted die and dynamic epistemic uncertainty with like the cards. So a Pomdp can model all of that without much trouble by saying that there's a transition probability that the internal parameters will change. So that's what the transition probabilities model. We just said that the state transitions were the state transitions for the internal states were deterministic and static for this particular case, but there should be no problem modeling that. Now, the harder question is, how do you estimate what that model might look like? Like, how often do people change? And I think that's kind of a harder problem. But once you had a model, then this tree search method could definitely solve it. So these, I'm going to skip over that. Any other questions about this result? Okay, cool. All right, so the problem is solving these things is really hard. So these might be POMDPs with continuous states, observations, and actions. And historically, people have only tried to approach POMDPs with discrete states, observations, and actions with these tree search methods. So we already talked about actually this POUCT or POMCP. Those are really names for basically the same thing. That can actually handle continuous states fine. And there's another algorithm called Despot, which is very good and very popular, that can handle continuous states fine. But once we get to continuous observations, it becomes a little harder. And this is where my work has come in. So if you put POMCP right on a continuous observation problem, like this light-dark problem, it actually will get, every time it generates a new observation, it'll generate a new belief node. So it'll be really wide branching factor for the belief nodes, because there's so many different possible beliefs that you could have based on the different observations that you can generate. You can artificially constrain this, but if you continue to use an unweighted particle filter, then you actually have this really bad particle depletion problem where every belief converges to a single particle, which also won't work. So if you do this on the light-dark problem, you'll get this problem where it will never be able to go, it's doing some greedy or myopic planning, and it'll never go up to the light region to localize itself. So we introduced a new algorithm called POMCP, and the innovation there was using weighted particle filters, which allows us to actually handle those continuous observation beliefs correctly and solve this problem correctly. So I would say the continuous observation problem, we've made a lot of progress on that. There's a few other algorithms called Despot Alpha and LabCop, which is something about lazy belief expansion, which use these weighted particle filters also, so they can handle continuous observations. Then the next challenge is continuous actions, which we've also done a lot of work on in the last year or so. This is a much harder problem because with continuous observations, you're just trying to calculate expectations with Monte Carlo simulations, whereas with continuous actions, you're trying to solve a nonlinear, non-convex, continuous optimization problem. So this is much harder. The most promising thing that we're working on right now is called Voronoi progressive widening, where you gradually add more action branches to your tree, and you sample these in a way that's more likely to put them in the Voronoi cell of the best performing previous action. So that's just like one quick taste of how you could do this on a continuous action space. And we showed that outperforms our previous kind of naive algorithm. And we have a nice theorem for it too. Okay, so that's basically like the algorithms you have at your disposal if you have a continuous state observation and action POMDP. And real quick, in the last 5 minutes, I'm going to talk about the open source software that we've built to make this easy. So we've built this library called pomdps.jl, which you could go and try this afternoon. And hopefully, if you wanted to, get it up and running and try these algorithms out. And the idea behind this library is to bring people who are writing problems, people who are writing solvers, and people who are running experiments together through a common set of interfaces. The reason we chose Julia, I'm not sure how many of you have heard of the Julia language, is for a couple reasons. Primarily, one reason is because of its speed. So it's a just-in-time compiled language, which means that it uses LLVM, the LLVM compiler, to compile. And if you look at basic benchmarks, it's much closer to the speed of C than MATLAB and Python are. And I think maybe the most impressive thing about the speed of this is what's called the Celeste project, which is where they use Julia on a supercomputer to achieve a speed of 1.54 petaflops. And the only other languages that have achieved this kind of speed are statically compiled languages like C, Fortran, or straight up assembly. So I think this kind of shows Julia's speed. We also chose Julia for its flexibility. So it's very easy to try something out and very easy to program new things in it. This is the website for a previous C++ framework, and they note this problem. So they say, we have these 3 different algorithms, but all the problems to be used by these 3 different algorithms have to be programmed up with a different interface. And they say, maybe one day that will be merged into a single coherent framework. And today I can tell you that that has happened, and that framework is pomdps.jl. So you can define problems either explicitly with probability distributions. So if you have a very simple PomDP, classical PomDP, 2 examples are the tiger PomDP, where you're trying to choose which door to open so that you don't get eaten by a tiger, and rock sample, which is like a grid world where you're a Mars probe and you're choosing to sample rocks. It's a very simple program that can have an explicit. But if you get something more complex, like the freeway driving problem, you have to use a generative model, which just means that you have a single step simulator. So instead of explicitly saying what the transition distributions are, all you have to do is be able to sample from that. And our solvers are able to work with kind of either one of those. And then my favorite thing is how simple the code turns out to be. So this is the pseudocode from the paper that describes the despot algorithm. It's got these 3 kind of functions in it for creating that online search tree. And this is the C++ implementation. So I worked with this, I dug into it very deeply to try and figure out how it worked and stuff and how to modify it. And then this is the Julia pomdps.jl implementation. So as you can see, it almost matches up line to line with these functions over here. And it's super easy to dive into, see exactly what it's doing, verify that it's doing what you think it is, and modify it. So we're pretty happy with that. Okay, so the last things I'm gonna cover are this kind of cheat sheet questions that Sylvia asked me to talk about. So one is, this is for online PomDP planning. So one is, when is this a good method to use? So I would say the answer to that is when reducing epistemic uncertainty can improve safety without sacrificing efficiency. So if you only have a safety problem, well, I guess that's the answer to the second question. If you only want to guarantee safety, these PomDP tree search methods are terrible for it, because there's a very big probability that your unsafe states will never get sampled. Whereas something like Hamilton-Jacobi reachability is a much better way to do that, because it says in the worst case, this set of states is never going to occur. But if you have epistemic uncertainty that you can learn about, and you need to make the system as efficient as possible without sacrificing safety, then it would be a great idea to combine these two ideas of worst case safety and probabilistic epistemic uncertainty so that you can learn to act efficiently while still staying inside these safety bounds. So that's when I would say it's most effective. What are the resources to learn this? So my advisor has 2 books that are really good. Well, I think they're really good. I might be biased, and very accessible. One is called Decision Making Under Uncertainty, which you can get on the IEEE website for free. And that's a really good introduction. And then the second one is Algorithms for Decision Making. So that's algorithmsbook.com. And you can just go there and look at the outline. And, you know, if I wanted to do Monte Carlo tree search, I would just look in online planning. And let's see, where is it? Right here is the algorithm. And oh wait, this is a surprise. All the algorithms in this book are actually written in Julia. So you can literally just copy and paste them and start off with that. So that's kind of a cool book. I still like this original Decision Making Under Uncertainty better. It's a little more accessible, but the algorithmsbook.com one is also good. To learn, I would recommend, or implementing them, I would recommend doing algorithmsbook.com or looking into pomdps.jl. We have a discussion board where you can ask your questions, or a lot of these algorithms, it actually pays, I think, to implement your own so that you understand it fully. Last, what are the major future challenges? So one, like I said, specifying reward functions is really hard. It's really subjective. How do you balance, you know, even beyond balancing safety and efficiency, how do you balance the rights of one person versus another? These are tough questions. Another one is tractable guarantees for uncertain systems. So you can formulate these problems as saying, like, the probability of collision is less than some small epsilon, but it's extremely hard to tractably calculate a policy that satisfies that guarantee. So that's a big thing that we're trying to work on here. And then if you don't have a good model for what other people are going to do based on data, then I think it's really hard to handle those situations. And that's what, you know, that's a big challenge in, for instance, autonomous driving. How do you handle the situation that you've never seen before? So I would say those are 3 big challenges. And with that, I'll turn it over to any questions. Thanks for listening. I went over time a little bit, sorry.
Thank you so much, Zach. If people have time, they're welcome to stay and ask questions. Otherwise, you could also, it looks like Zach has his website there where you could probably find out more and ping him.
Yep.
But if you need to get going, go ahead and get going.
So you brought up that it's an active kind of challenge, balancing safety and like performance in terms of structuring your reward. Do you have any like, in terms of how people kind of approach it right now, rather than just using some like base knowledge or some knowledge of the current models? Do you have any advice on how to kind of structure that for your problems and stuff?
Yeah, that's a good question. So I mean, there's the kind of go-to concept is called inverse reinforcement learning. Are you familiar with that at all?
Yeah.
Okay, so yeah, you could do some kind of inverse reinforcement learning that trades off different objectives, like different parts of efficiency. You know, is it time efficiency? Is it gas efficiency in autonomous driving? Is it, you know, for a cancer treatment problem, is it, you know, getting the treatment done as fast as possible, or having it be, you know, have less side effects? So inverse reinforcement learning might be one way to do that. But so the other way to look at it is this. So on these Pareto curves, you might not know where someone wants to be. But if you come up with a good algorithm, if you have a good model that models epistemic uncertainty correctly, and a really effective algorithm, then you can improve it so much that if they're with the old algorithm, like say their true position is here, and you're able to improve this algorithm, then they would prefer everything from like, no matter where they are on this part of the curve with the old algorithm, they would prefer like a huge part of the new curve for the new algorithm. So I think in practice, what we want to strive to do is make algorithms that are so good that people will prefer them no matter what their kind of different weighting is.
For context, Nikhil is the one that I mentioned to you who's thinking about like safety with surgical robotics and how much to push tissue.
Yeah.
So.
Cool. Yeah. So yeah, I mean, in that case, like if you have a good algorithm and a good tissue model that if you push it a little bit, you can like learn how it might react in the future, you can reduce that epistemic uncertainty, then you can make an algorithm that's both so much more safe and efficient that it doesn't matter exactly what their weighting lambda is. They'll prefer that.
Okay. And one more thing is, I guess, in regards to starting off your particle belief, like, is there any good way to choose priors? Because sometimes when you, if you want to be a bit cautious in the beginning, I guess, one thing I was struggling with is like thresholding my priors so that like it's not way too like apprehensive about doing anything versus it's too over optimistic about the environment and goes into an unsafe regime.
Yeah, that's a good question. And yeah, choosing priors is really hard. So what I would do is my initial thought, I haven't thought about this too much, but my initial thought is choose a really conservative prior and make your belief updater really good, or as good as possible. So like have the highest entropy prior you can think of, but then like try and get the most observations and try to have the best probabilistic model for that allows you to reduce uncertainty with new observations rather than trying to pick the exact right prior. So I guess I would listen to observations more than try to make and find algorithms that care more about the observations than the prior.
Okay, thank you.
Yeah, cool.
Stop.
All right.